thanks for the nice introduction. And yeah, also for the organizers for this very nice meeting and for giving me the chance to present some of our work. So, as Nadezhda just said, I just recently moved to Munich. So I was in Vienna before, and since February now I'm located at the TUM and at the Walther-Meißner-Institute. And let's say today I talk about some activities and projects which developed still in Vienna here, but now actually it's on the theory side. But okay, now also at the Walther-Meißner-Institute there's some experiments which you already heard from Kirill, where we might be able actually to implement some of these things that I will talk about today. Okay, and I just also want to point out, so the main guy behind all these results I present is my PhD student, Joan Augusti here, okay, who did really most of the work I'm presenting today. Okay, so I will continue with the topic of quantum networks and maybe from a slightly different perspective, okay, coming maybe from superconducting quantum computers. So you hear all the news, people, Google, IBM, they're now building quantum computers with many 100 qubits, and for sure we will see quantum processors with a few thousand qubits in the coming years. And these type of systems, can essentially still pack into a single fridge and scale up everything within a single fridge. Okay, but if you think about going down to millions of qubits, it's clear that there's not enough space here. So probably what will happen on a longer time scale is that you take this superconducting process with a few hundred or thousand qubits and then integrate them into something like a quantum local area network. Okay, so to trying to build this, attach these fridges to each other, and then of course you have to care about communicating quantum states or distributing entanglement within such small local area networks. But also more generally, eventually you might want to take your superconducting quantum computer and connect it to the quantum internet, and then distribute quantum states over larger distances, and then you might take these microwave photons, you upconvert it into optical photons, and over longer distances you have to do optical communication, and also then to distribute quantum states along across the city, or maybe even further once we have quantum repeaters. Okay, so this is the thing that we certainly maybe don't want to do right now, but maybe in a 5 or 10 years time scale. And then the question is, how do we do this? And this question, is also quite old. And if you probably noticed this paper here by Ignacio Sirac and Peter Zoller and Kimball. And they essentially showed that, in principle, once you have a qubit, local qubit, and you can couple it to some waveguide, some optical waveguide, it can emit a single wave packet that encodes the quantum state, and there's actually a protocol to perfectly reabsorb this photon wave packet. Okay, and in principle, this is enough to transfer a quantum state, a superposition state, from one place to a distant one. You can also then use some optical transducer to convert microwaves into optics, and then really have this interface for everything what we in principle want. Now, of course, if you look at the implementation of such ideas, of course you need to, you have to catch these wave packets. Okay, you need to have a high level of control. Also, you make sure that nothing is lost. Okay, you have less than 50% losses until you lose all entanglement properties in the systems. And once you go to these optomechanical transducers, these devices are typically very low bandwidth. Okay, so the speed of such a thing, once you convert to optical photons, is not very large. So there are other schemes you might have heard of about probabilistic entanglement distributions. So very roughly, the idea is you have a local qubit here and here. You create a weak interaction with a photon state. So most of the time you don't do anything, but sometimes you create a photon. The photons propagate to some beam split in the middle. They can also be lost in between. And most of the time you simply don't do anything. But once a photon makes it through, it doesn't, you don't know from which place it comes. And therefore, the state that you get conditioned on a photon click is then an entangled state. And these schemes are much more robust with respect to entanglement, but of course also because you have to try many times and the probability to get a click is very low, these are, again, the efficiency is not very great. So what I actually want to point out here, is a little bit, if you talk about, or these days, if you think about talks about superconducting or quantum computers in general, you hear people talking about many tens of qubits, many hundreds of gates, fidelities, incredible 10 to the minus 3 gate fidelities. commercial devices and so on, if you go to the problem of quantum communication, we're still far behind such capabilities. So you usually talk about, okay, entangling 2 qubits, fidelities are then more in the 90% or so. Often we talk about entangled pairs per second and so on. So there's still kind of a huge gap between what we can do, let's say on the computation side, and what we can do on the quantum communication, quantum networking side. So I think this is, let's say, one type of message here I want to convey, also for people here, for the students here in the audience. I think this is still an open problem to efficiently interface quantum networks or quantum processors over small and larger distances. Okay, so in the following talk, I will actually not give you the final solution to this problem, but some approach which I find quite interesting. And this type of idea actually go back to also a quite old paper by now from Barbara Kraus and Ignacio. And this is here the idea is not to do a state transfer, but let's say just to distribute entanglement. And the basic idea is, let's use two-mode squeezed light here as a source for entanglement. So two-mode squeezed beams, it's a photonic correlated state, entangled state, but now with a lot of photons in there. Okay, now it simply takes these photons and send them to these two distant qubits and illuminate these qubits with correlated entangled light. And in principle, we might say, okay, so these beams now contain a lot of photons, okay? So we have a bosonic Hilbert space, a lot of excitations in there, and then we shine it on a two-level system, okay? So this will just give you a lot of mass. But it turns out, if you then do the analysis of this type of schemes, and there have been others around, find that actually the steady state of the system is, first of all, a pure state, and an entangled state. And this entangled state, if you have just crank up the power, have more and more photons, actually approaches a maximally fully entangled Bell state. Okay, so these are, again, these are some ideas which are also then have been reinvestigated throughout the literature. This type of scheme or this prediction, is still based on several approximations. So let's say when we looked at these things first, we were interested on, okay, so how can we actually, does this still work in finite so let's say in realistic networks when you have propagation, time delays, finite bandwidth, and so on. Okay, but it's actually what I would like to talk now a little bit today is actually then some generalization of these ideas, and now going from, let's say, from 2 qubits, so think about scalability. Okay, so I will talk about now systems where I again have this two-mode squeeze state, I generate correlated photon pairs, but then I send it along waveguides, and these waveguides contain now many qubits in each arm. And what I will hopefully manage to show you, convince you that this scheme, has some very interesting features that I think on the long run can also really be relevant for this quantum communication task. Okay, so just to give you a little bit ideas of what we're considering. Okay, so we consider now this abstract network. Okay, so we have we have some nonlinear process here. So this is a parametric amplifier, non-generated parametric amplifier, which simply means I drive a nonlinear crystal or some other nonlinear device with a strong bump beam, and then it generates photons with frequency omega A and omega B through this pair creation interaction. Okay, so then you create correlated photon pairs, and these photons then decay in the respective waveguides and then propagate along and interact with these qubits. So what I will also assume is here that these qubits are now coupled to this waveguide in a directional manner. Okay, so as photons come in, they can excite this qubit all the time. The qubit gets excited, it can decay back into the waveguide, so it's constantly on coupling. And I assume that, let's say, then the photon that decays propagates along the same direction as the incoming photon. There are several ways you can do this using circulators, chiral waveguides, and other type of non-reciprocal elements. So, but yeah, for now I will not go into implementation, but just assume that I have this directional coupling. Okay, so then let's say in the first step, okay, we can now think, okay, how do I model this? And in the first step, I can see, okay, so these photonic modes, they can assume that they decay very fast. Okay, so broad bandwidth, which is essentially much larger than the decay rate here. And in this limit, I can essentially eliminate the photon degrees of freedom, and then the qubits interact with a two-mode squeezed reservoir. Okay, maybe just very quick, I mean, yeah, so maybe I don't go into detail. I mean, in the end, you can write down a master equation which has this cascaded interaction Hamiltonians and this correlated operators. So in the end, just maybe to show the slide, and now we have some dissipation processes here which are described now by collective operators, that destroy a collective excitation along a single waveguide, and at the same time they create a collective excitation at the other waveguide. Okay, that's these typical squeezing type of correlations, and the squeezing parameter here, this parameter R, is determined by my parametric amplifier by the coupling over the waveguide couple. Okay, but I think I will not go into much detail here about the formulation, but okay, so what is the problem I want to solve? So now I have this reservoir, okay, I have these photons constantly switched on, okay, so they will always interact with the atom will scatter, yeah, and I have a lot of dynamics going on, and then I simply wait until my system reaches the steady state. Okay, and now the question is, what is the steady state? And in principle, it's an open quantum system, multi-qubit system, so you don't expect anything crucial to happen, just a big mess. But okay, so let's go into detail and approach this, okay, going back to the case where we just have a single pair, okay, and that reduces to essentially the configuration I had in the very beginning. And okay, you can go back to this paper or also solve it yourself. I mean, it's then not too complicated. And you find that the state, indeed, as I said before, the steady state of the system of the qubits only is a pure state with the superposition of 0, 0 plus 1, 1 if the squeezing parameter is on the order of 1. Okay, so you don't need to squeeze arbitrarily large, but if this is on the order 1, you're almost perfectly entangled. Okay, so this is something you can actually calculate, can calculate and then convince yourself that's the steady state. But actually what I would like to emphasize here or talk a little bit quickly about, I mean, how to think about this state. It's quite a strange object. And for this, I mean, think about this, again, this two-mode squeeze state, which you probably know. So two-mode squeeze state is a state where always pairs in the two modes come correlated, okay? You have 5 photons in one arm, you also have 5 photons in the other arm. And then you have a superposition of all these combinations. So then I have, let's say, this two-mode squeeze state, and this two-mode squeeze state will then couple to the qubits, okay? And now I assume just a single mode James-Cummings type interaction, so you have a James-Cummings type, you emit the photon, so you destroy excitation and qubit, and then create a photon in the waveguide. So the thing is, if you now look at this state, okay, so this combination over here, which I just told you that this is the steady state of the system, you actually find that then if you apply this interaction Hamiltonian to this combination, okay, so this qubit state over here multiplied by this two-mode squeeze state, then this interaction acting on this state gives you 0. Okay, so there is a kind of a destructive interference effect, and I think the interesting part about it, so if you think about what interferes, then you have a process where you emit a photon in waveguide A, and there's another process where you absorb a photon in waveguide B that is at the other end of the universe. And these two processes, they interfere. So it's a very strange concept, but this is possible because you're not working in a vacuum, okay, so there are photons present in both waveguides, and they are correlated over these distances. Okay, so this means, okay, you have to think about this steady state as a dark state, okay? So once the two qubits are in this state, then they decouple, so the interaction gives 0, so they decouple from the waveguide. And this you can now also use to now investigate larger systems, okay? So I have this two-mode squeeze state, it scatters from the first pair of qubits, there will be a lot of scattering, but eventually these two qubits will go into this dark state, where they they couple from the waveguide, okay? So then we have this state, and they are essentially out of the picture. So then the next two pairs of qubits, they see again a two-mode squeeze state. So the same thing happens, okay? They are driven by the squeezing state, they will go into dark state and essentially disappear from the coupling. So and this means that you can do this, make this argument and see that, even if you just have a single source here, in principle, you can use this mechanism to entangle an arbitrary number of these qubit pairs. Okay, so, I mean, this is a first very interesting conclusion. I mean, one thing that you can also convince yourself is that the same thing happens, is still possible if you slightly detune the qubits. Okay, so far everything was on resonance scattering, but if you detune this qubit by delta 1 and the other one by minus delta 1, and always kind of pairwise, nothing changes. Okay, this state is still a dark state of this interaction. It doesn't evolve under this combination, this balanced detunings. Okay, so now, but let's say now the question is, so you see that this guy is now entangled with this qubit because they have the same, the delta and minus delta. So, but what happens, you know, if I now, for example, exchange these two detunings? Okay, I detune this to minus delta 3 and this to the minus delta 1. So then, you know, the question is now, I mean, is it actually now that this qubit is entangled with this one, or is simply everything, you know, a big mess because I messed up, let's say, this dark state condition here. And okay, so this problem can now be, you know, we can address it and look now at the structure of these cascaded systems, and without now going to detail, so what is the conclusion that we draw from this? Okay, so the thing is that these type of cascaded master equations, they have a certain property, which we then call form invariance here. And what does it mean? Okay, so suppose I have now a large array of these qubits with a certain pattern of detunings, okay? And suppose you know that for this configuration, I have a steady state, a dark steady state, which I call psi 0. Okay, so suppose you have figured this out and found this state. Then the statement is that if I now take another configuration, everything the same, except two neighboring detunings here in this waveguide B are exchanged. Then if I have this configuration, I know that there's again a dark steady state that's related to the previous one by just this unitary operation. And what is this unitary? So this unitary is now a combination of identity plus a swap operation. Okay? And the mixing between this mixing angle is determined by the frequency difference. So if I go back to the regime where all the detunings are the same, then this is 0, and I just have identity, nothing happens, okay? If I go to a regime where the detunings are very far apart, then I just get a swap, okay? It's maybe a trivial swap operation, but for any arbitrary detunings, I get, you know, nothing happens plus a swap operation. So this is a square root of swap operation. You think about this. So this creates an additional entanglement along the waveguide axis. And this type of ideas I can now, this was now the statement I made, and now I can actually, you know, construct me a large family of entangled states. Okay, so think about, okay, this configuration for n equal 4 qubits, and this is kind of what I told you before. So if we have always pairwise opposite detunings, we have these product states of pairwise entangled states. Okay, so this is what we know. So now we want maybe a waveguide configuration where the detunings in the waveguide B are a permutation of these detunings. Okay, so delta 4 is here, delta 2 is and so on. And now the question is, okay, what is this steady state? And given this type of prescription I told you in the previous slide, okay, we can now do this systematically. Okay, so in the first step, I find I take this permutation from this detuning to over here and decompose it into pairwise transpositions. Okay, this is always possible, and I find these transpositions. And then according to this previous statement I made, each of these transpositions I can then take the corresponding unitary, and then with this prescription I can construct explicitly this dark state of this new type of configuration. And because these unitaries, I mean, they generate also entanglement, they create entanglement between the pairs, so this is a complete multi-partite entangled pair, which is kind of determined by the set of detunings and the permutation I use for these detunings. Okay, so just a very quick example. Okay, so in the easiest case, so if we've just now two pairs, okay, think about this type of configuration. So in this case, the only thing I can do is, okay, I take these two detunings the same, or I swap them. Okay, so and then in general, the only parameter I'm left with is this detuning, the difference between the detunings, and then I can explicitly write down the steady state. Again, it's a pure state with kind of one component which is parallel entangled and one component that is kind of cross entangled, and of course we have a superposition here in general. Okay, so detuning very large, I'm in this limit, detuning very small, I'm in this limit, and if I'm detuning at about 1, I have, all these combinations, and I can show, in this case, it's really a genuine four-partite multi-partite entangled state. And again, I mean, as I also mentioned before, if you look at how all this depends now on the squeezing parameter, we want to have really high entanglement. We don't need to go crazy. We need squeezing parameters around 1, but, not super crazy to get all these ideas. Okay, so so I mean, let's say this for 4 qubits we can still write down and this everything and discuss it. Then of course for multi-partite systems, it's also not so easy to characterize multi-partite entanglement. That's still an open problem how to characterize it. But let's say roughly speaking, I can think about now. Depending on your tuning patterns, so again, you can have just create a bunch of pairs. If you have the detuning, everything far detuned, and you exchange them, then you just change the order. But once you have detunings that are around gamma, then simply if you do this, you also generate a lot of multi-partite entanglement. And with this type of flexibility, within the same setting, same squeezing source, you can generate. Actually, you can program the type of multi-partite entanglement that you actually want without doing any other things or other adjustments. Okay, so I think at this stage, I'm telling you that I have, everything I did so far, I mean, is independent of the system size. Okay, so I can have an arbitrary number of multi-partite entangled state. But let's say what I haven't told you, this is a steady state. So what I haven't told you is how long does the system actually take to reach the steady state. Okay, if this takes an exponential time, it's not very useful. So, but here we can now also, we can do some small scale simulations, and this would be now kind of the preparation time. If I let the system run and how it reached the steady state. So now this for this configuration, and we simply calculate the concurrence of each of these pairs, and we simply see as expected, the first one goes in the entangled state, and the second one, and so on. And we see if we plot this time now, how long it takes to reach the steady state as a function of n, the number of pairs. It's really a linear scaling. And interestingly, already this linear scaling, is a little bit faster than actually what you would do if you prepare these states, one by one after each other, because you have all the dynamics here already takes place before this reaches steady state, so you have a small intrinsic advantage. But interestingly, if you now increase, you have a detuning pattern where all the pairs are detuned, you find that you actually get an additional speed up, and eventually, if the detuning is gamma or 2 gamma in this order, you actually find that the preparation time is independent of the number of pairs. Okay, so in this limit, we achieve a situation where we can prepare an arbitrary number of qubit pairs in a finite time. Okay, so that's kind of the prediction we get out of this plot. Okay, now of course this sounds a little bit suspicious. Okay, infinite amount of entanglement, finite time. So what is the catch? And maybe you have paid attention. So what I did so far was always I analyzed the system under the assumption that my two most squeezed source is a Markovian reservoir. Markovian reservoir means infinite bandwidth, and this also means an infinite amount of photonic entanglement that I start with. Okay, so but let's say in any finite system, this bandwidth will also be, these correlations will be finite. Okay, and if of course if I then detune my system over here, there will not be any entanglement left. So, but this means, from a theory point of view that, okay, I cannot make any meaningful prediction without taking this bandwidth effects into account. And this then also makes this, so I need to simulate the full system to make any meaningful predictions. Theory-wise, it then becomes a little bit messy because I have to simulate 2 modes and 2 n qubit pairs, okay, a master equation of this, so we can only do very small systems at this case. But in the end, okay, we can at least do some estimates. And essentially what you see here is now the concurrence, the entanglement as a function of number of pairs, if I have now a finite bandwidth effect. Okay, so previously this was always constant, but you see if I now change the ratio, okay, so this beta is the ratio of kappa over gamma. So if I change this ratio and have it finite, there will always be a small decay. And this decay then will, for example, if I take the slope here, I can say when will this reach actually 0? So what is the maximum number of entangled pairs that I can achieve? And this I can then put into this plot. And again, I mean, if I look now at otherwise ideal conditions, so no dephasing and so on, I really see that, for moderate values of this bandwidth, it has to be larger, but a few times larger, I can really, this entanglement number would really be a few tens or even 100. If I have imperfections, okay, there are other things, dephasing, local dephasing, that will set a limit, but in principle, the scheme is still, without going to too crazy numbers, you can should be able to entangle many tens or hundreds of qubits. Maybe then final conclusion, maybe just to make the statement, if you then do a different estimate and think about this bandwidth effect, actually you also find, okay, so I mean, due to this finite kappa, okay, we have a finite number of pairs that we can entangle, but it actually turns out that under the same condition I can entangle these 100 pairs, I can also entangle them more or less in parallel. Okay, so this bandwidth, it gives you a limitation, but this parallelization that I talked to you about within this number is actually still intact. Okay, so this is, I think, then also the important conclusion. So we get a finite value, but we still get an intrinsic parallelization effect once this amplifier bandwidth is sufficiently large. Okay, yeah, and for this, so to stay in time, so let me just summarize these ideas. Okay, so I think it's a kind of a new type of approach to really distribute also now multi-partite entanglement. I think the thing is, okay, on one hand, it's autonomous, you don't need any time control, and you really also can use it to do multi-partite entanglement, and this, you can really program by simply changing the detunings, so without doing any other settings. As I just, I was a little bit quick in the final slide, but in principle there is intrinsic parallelization type built in this type of schemes. And I think what I also want to emphasize that these two-mode squeeze states, I mean, they exist in optical and microwave. You can also have hybrid systems, photonic squeeze states. So in principle, this scheme is very generic, and I think you can apply it to various type of systems, which I didn't talk here. Okay, with this, thank you for your attention. And I'm happy to accept questions.
Thank you, Peter. Questions, please.
Yeah, thank you very much. I have a question about near the very end when you mentioned master equations which are difficult to simulate.
Yep.
Could one use tensor network methods for that? Have you thought about that?
Yeah, so we tried some slightly non-standard methods also to do this. In the end, the problem is with, so if you go away from this infinite bandwidth limit, you also start to generate entanglement across the chain. Okay, so in the initial state, we thought, okay, we have essentially this pairwise entanglement, and then matrix product state should be very, very, very useful. In the limit where then this kappa is finite, you also generate entanglement along the chain, and at least
well, that's what those matrix product states are made for. They capture entanglement along the chain.
Yeah, but it's then, because the photons propagate across the whole chain, so it can then be quite a lot of entanglement. So, I mean, the statement is the way we tried it, not extensively, it was then a little bit limited, so we didn't get very far with these type of methods.
Well, I would recommend following up on that. So,
yeah, no, I mean, there's certainly room to play around, and yeah, thanks for the suggestion.
Yeah, thanks for the really interesting talk. I really like this proposal. I have a question about timescales also. So you quantified the preparation time, and for this, if I understand correctly, you need these atoms to have a finite decay rate. And I wonder, can you also say something about the lifetime then of the state that is produced? Or is the idea that the decays are can be switched, or is it?
So at this stage, I just look at the steady state. Okay, I have the qubits always on to the waveguide, and this gamma here that sets the timescale is the coupling to the waveguide. Yeah? And of course, I mean, eventually you want to prepare the state and then use it for something. So then maybe you transfer it to other qubits that are not coupled, or you switch off the coupling to the waveguide. But everything I do here now is steady state, and this waveguide coupling is the relevant timescale here. Yeah.
Okay, thanks.
Thank you very much for the very interesting talk. I have a question regarding then, how to say, the dark state. If we consider the experimental imperfection and partially, in particular, the if the coupling strength to the waveguide is a little bit asymmetric between these two parties. Can you comment about this?
Okay, now I would need to think, I mean, roughly speaking, I think it's not, so the coupling to the waveguide is probably not that crucial. Okay, so I have to say maybe I should think about it before I make this statement. I mean, here, let's say this argument I presented, this was kind of, you have the same coupling to both waveguides. If you have now different couplings, whether then you simply change this constant here, I don't want to say anything wrong now, yeah. I don't think it's super crucial to have the same. So we did also different decay rates here, so slightly asymmetric squeeze states and so on, so it was not, did not affect the scheme, and I don't expect it to be crucial, yeah. But maybe I shouldn't make a definite statement here now. Yeah.
Okay, thank you, Peter. So if you have more questions or you want to discuss, please find Peter during the coffee break. And let's thank speaker again.